Welcome everyone. Myself, Dr. Shimpi Ralhan, Professor Shishankracharya Technical Campus, Bhilai. Today, we are going to delve into an interesting aspect of drive systems that is important for modern engineering applications, the four-quadrant operation of drives. Four-quadrant operation allows drive systems to perform efficiently under diverse conditions, supporting forward and reverse motion as well as active braking and energy regeneration. These capabilities are increasingly vital in applications ranging from automotive to industrial automation. So, we will start by examining torque equation for the electric motors to understand how these foundational elements contribute to four-quadrant operation. Following this, we will discuss bidirectional electric drive systems and what exactly four-quadrant operation is, including its significance and the benefits it brings to industries. Have a look at the importance of the four-quadrant operation and its industrial significance. Moving forward, we will also explore the technical aspects such as the role of converters and controllers and delve into sophisticated control strategies like vector control and direct torque control. So let's begin. Electric motors exhibit a variety of speed torque characteristics that are suitable for a wide range of load demands. A single motor can exhibit different speed torque characteristics based on its winding configuration or the characteristics of the electric supply. Now let us discuss the fundamental torque equation for the electric motors, which are integral part of drives. A motor generally drives a load, say machines, through some transmission system. While motor always rotates, the load may rotate or may undergo a translational motion. Load speed may be different from that of motor, and if the load has many parts, their speeds may be different, and while some may rotate, other may go through a translational motion. But we represent the motor load system by an equivalent rotational system, as you can see. This system is based on force torque analogy and used for deriving the torque equation. Let us see what are the various notations. Here J is the instantaneous moment of inertia of the motor load system referred to the motor shaft. Omega is the instantaneous value of the angular velocity of motor shaft. T is the developed torque by the motor. Then TL is the instantaneous value of the load, or it is, you can say, the torque resisting the motion, and it is referred to the motor shaft. The motor load system of the figure can be described by the following fundamental torque equation. Load torque includes both the friction and the windage torque of the motor. Now, as you can see, the difference between the torque and the load torque is given as a time derivative of product of J and omega m. So, if we differentiate that, we will get J d by dt of omega m plus omega m d by dt of J. This equation is applicable to variable inertia drives such as mine winders, reel drives, industrial robots, etc. For drives where dj by dt is equal to 0, means that the inertia remains constant. So, T minus TL is given as J d by dt of omega m. So, this equation shows that the torque developed by the motor is counterbalanced by a load torque TL and a dynamic torque J d by dt of omega m. The torque component J d by dt of omega m is called the dynamic torque because it is present only during the transient operation. Drive now accelerates or deaccelerates depending on whether T is greater or less than TL. During acceleration, motor should supply not only the load torque but an additional torque component given by J d by dt of omega m in order to overcome the drive inertia. In drives with large inertia such as electric trains, motor torque must exceed the load torque by a large amount in order to get adequate acceleration. In drives requiring fast transient response, motor torque should be maintained at the highest value and motor load system should be designed with the lowest possible inertia. The energy associated with dynamic torque J d by dt of omega m is stored in the form of kinetic energy given by the expression 1 by 2 j omega m square. Now, during deceleration, the dynamic torque, which is J d by dt of omega m, has a negative sign. Therefore, it assists the motor develop torque T and maintains the drive motion by extracting the energies from the stored kinetic energy. So, the speed of the system is not determined by the motor only, but it is also heavily dependent on the load characteristics. Hence, the characteristics of the load cannot be ignored when we are designing an effective electric drive system. Now, let us have a look upon bidirectional electric drive system. They are capable of operating in both the forward and reverse directions. This flexibility is essential for applications that require reversible operation without the need to manually switch the mechanical setup. Now, consider the case of an electric motor driving a mechanical load in a steady state operation. A force exerted by either part of the drive system, load or motor, is opposed by a force equal in magnitude and opposite in direction from the other. If a frictional force is present, it is part of the load force, and this is true for any drive system even in standstill condition. In drive applications, classifying the action and reaction forces is not always obvious. Either part of the drive system can produce an action force depending on the nature of the operation. So, let us consider an example as shown. An elevator is moving the passengers in both the directions, that is up and down. For simplicity, let us assume that the elevator does not have a counterweight. So, in the upward and downward directions, the motor sees the load torque FL, which is function of the weight of the passengers plus elevator cabin cables and so on. Since the weight and FL are unidirectional, the motor force Fm is also unidirectional. The speed of the motor in this operation is though bidirectional. So, this is a very important point to be noted that we see here with the help of this example. Let us see another example. The figure here represents an electric bus which is driven uphill then downhill. To simplify the system, assume that the electric motor is directly mounted on the front wheels of the bus. Let us first study the system motion in the uphill direction. The force of the load is divided into two components. One is perpendicular to the road, F, producing the frictional force, and the other FL is parallel to the road and represents the load torque exerted on the motor. The direction of FL depends on the orientation of the road with respect to the gravitational force. FL always pulls the bus towards the base of the hill. If frictional forces are ignored, the load torque seen by the motor is FL multiplied by the radius of the wheel. This load torque must be matched by a motor torque Fm in the opposite direction to FL. Now, let us assume that the bus is in the downhill direction. Because of the gravitational force, FL still pulls the bus toward the bottom of the hill. However, as you can see that the motor, in this case, the load force is reversed. That is, the motor torque must then change its direction to counterbalance the torques of the load. It is to be noted here that the motor speed is unidirectional in uphill and downhill motions. Only the torques of the systems are reversed. So, now as we have discussed about the active and passive load torques earlier, both of these can be present in general in a drive system. The motor driving the load may operate in different regimes, not only as motor but for specific periods also as a generator and as a brake. In many applications, the motor may be required to run in both the directions, as we saw in case of bidirectional system. Therefore, in sketching the speed torque characteristics of either the load or the motor, it is preferable to make use of all the four quadrants of speed torque plane for plotting rather than to confine the characteristics to the first quadrant alone. So, here comes the concept of the four quadrant operation of electric motors. This four quadrant operation, what does it refers to? It is the ability of a drive system, particularly motors, to operate in all the four quadrants of torque speed plane, and this capability is very critical for precise control of motor speed and direction under varying operational conditions to which the motors are subjected. Now, the four quadrants represent different combinations of direction, that is, it can be forward, it can be reverse, and modes, motoring mode or braking mode, that the motor can operate in. So, quadrant 1 is the forward motoring. Here the motor runs in the forward direction and drives the load. Quadrant 2 is forward braking. In this quadrant, motor runs in the forward direction but deaccelerates the load, typically using regenerative braking. In quadrant 3, reverse motoring happens. The motor in third quadrant runs in reverse direction, driving the load backward. Quadrant 4 is reverse braking, and in this quadrant the motor runs in reverse direction and deaccelerates the load. So, these are the four quadrants and how the motor operates in each one of them. If we see the graphical representation of each quadrant, then we can say that a two-axis graph is plotted where the horizontal axis represents speed and the vertical axis represents torque. Each quadrant reflects a unique combination of these variables, positive speed and positive torque for quadrant 1, positive speed and negative torque for quadrant 2, negative speed and negative torque for quadrant 3, negative speed and positive torque for quadrant 4. So, this graphical tool, as you can see, is essential for visualizing the operation of the drive and understanding how changes in control parameters affect the performance of the motor. Now, let us see the conventions used for positive and negative values of speed, motor torque and load torque, which govern the power flow analysis of electric drive systems in the four quadrant operation. The speed is assumed to have a positive sign if the direction of rotation is counterclockwise or is in such a way to cause an upward or forward motion of the drive. Remember this, that the positive sign convention for speed is taken in this condition. In case of reversible drives, the positive sign for speed may be assigned arbitrarily either to counterclockwise or clockwise direction of the rotation. The motor torque is taken positive when it causes an increase in speed in the positive sense, and the load torque is assigned a positive signs when it acts against the motor torque. You can see the four different modes of operation of an electric machine in figure A. Although the diagram indicates that the field polarity is maintained and the armature current is reversed to obtain negative torque, the same effect is obtained by reversing the field polarity and maintaining the armature current direction. Field reversal is necessary with some forms of rectifier control. Both AC and DC rotating machines can operate across all the four quadrants, but DC machines transition between quadrants more smoothly and perform reliably throughout their entire operating range. So, DC machines are preferable. The four-quadrant operation of a motor driving a hoist consisting of a cage with or without load, a rope wound onto a drum to hoist the cage, and a balance weight magnitude larger than that of empty cage but smaller than that of loaded cage is shown in figure B. The arrows here indicate the actual direction of the motor or electromagnet torque, load torque and motion in four quadrants. So, here the arrows correspond to sign conventions as we saw for speed, motor torque and load torque. So, you can correlate between the two. The load torque of the hoisting mechanism may be taken to be constant, that is, it is independent of speed. Forces due to friction and windage are negligible in case of low speed hoist, and the torque is primarily due to the gravitational pull on the cage. This torque, being an active load torque, does not change its sign even when the direction of rotation of the driving motor is reverse. Therefore, the speed torque curves of a hoist load can be represented by means of vertical lines passing through the two quadrants. The speed torque characteristic of a loaded hoist is shown in figure B by means of vertical line passing the first and the fourth quadrants. Since the counterweight is assumed to be heavier than the empty cage, the inherent tendency of the load with the empty cage is to move in an opposite direction to that of load presented by the loaded cage, and hence the speed torque curve of the unloaded hoist is represented by the vertical line passing through the second and third quadrants. Thus, you can see the vertical lines which are passing through first, second, third and fourth quadrants. Let us now see the operation in all the four quadrants one by one. In the first quadrant, the load torque acts in a direction opposite to that of rotation. Hence, to drive the loaded hoist up, the developed torque in the motor M must act in the same direction as the speed of rotation, that is, Tm should be of positive sign. Since the speed is also positive, being an upward motion, the power will also have a positive sign. That is, the drive is said to be in motoring mode. Quadrant 1 is arbitrarily and conventionally thus designated as forward motoring quadrant. Since speed and torque are both taken as positive when motoring forwards, upwards or counterclockwise, the product of E and I is taken as positive under these conditions. Remember this point, it is very important. It is conventional to assume that both E and I are positive under this condition, that is, we assume the flux to be positive, so that positive E corresponds to positive speed and positive I corresponds to positive torque. If in all the circuits the direction of the current in the field winding is assumed to be same, the flux is automatically positive. Then the negative armature current indicates what? It indicates a negative torque, that is, the torque in the reverse, downward or clockwise direction. Similarly, negative EMF indicates negative speed. So, to avoid all these difficulties, it is required to maintain these conventions consistently in the circuit analysis, and the signs will indicate the mode of operation. The motor equation shown, that is V is equal to E plus IR, must of course be used consistently for all cases, and no attempt should be made to prejudge the behavior by using the generator equation given by V equals E minus IR at any time. So, always we will be using the equation V equals E plus IR. After completing the quadrant 1 operation, let us see what is quadrant 2 operation. The hoisting up of the unloaded cage is represented in the second quadrant. Since the counterweight is heavier than the empty cage, the speed at which the hoist is moved upwards may attain a dangerously high value. In order to avoid this, the motor torque must act in a direction opposite to that of rotation. That is, the motor should switch over to braking or generator regime. Note that Tm will have a negative sign and speed still has a positive sign, being forwards, upwards and counterclockwise. Thus, power has a negative sign corresponding to the generating or braking operation. So, now let us see the third quadrant. It represents the downward motion of the empty cage. The downward journey of the cage is opposed by the torque due to counterweight and friction at the transmitting parts. So, for moving the cage downwards, the motor torque must act in the same direction as the motion of the cage. The electrical machine acts as a motor. So, for moving the cage downwards, the motor torque must act in the same direction as the motion of the cage. So, the quadrant 3 becomes a reverse motoring mode. The motor torque has a negative sign as it causes an increase in speed in the negative sense, and the speed also has a negative sign being in the downward motion. Power thus has a positive sign as both the signs, that is the motor torque and the speed, are negative. Now let us see the quadrant 4 operation. The downward motion of the loaded cage is shown here. The motion can take place under the action of the load itself without the use of any motor. But in order to limit the speed of the downward motion of the hoist, the electrical machine must act as a brake. The motor torque has a positive sign as it causes a decrease in speed in the downward motion. The speed has a negative sign being a downward journey. Thus, the power acquires a negative sign corresponding to reverse braking operation of the motor. So, after the complete discussion of the 4 quadrant operation, now let us discuss its importance. It has a great significance in industrial applications and in many key industries such as transportation, robotics and manufacturing. For transportation, the 4 quadrant operation is important in vehicles for enabling both acceleration and regenerative braking, which captures energy during deceleration and feeds it back into the system. In robotic systems, the 4 quadrant operation provides the ability for robotic arms and machines to move fluidly and precisely in any direction with the capability to accelerate, decelerate and hold positions under varying loads. If we talk of manufacturing, the 4 quadrant operation enhances automated processes by allowing machinery to operate more dynamically. This is done by adjusting the speeds and directions quickly based on the production needs. So, the 4 quadrant operation has many benefits for control and efficiency too. We will be focusing on 3 main areas, that is enhanced control, increase efficiency and operational flexibility. First, let's talk about control. The 4 quadrant operation offers unmatched precision in both speed and torque control. This level of control is absolutely critical in industries where high accuracy is essential. Imagine robotic surgery or high precision cutting machines. Here, even a minor deviation can lead to significant issues. So, the 4 quadrant drives ensure that the machines operate exactly as intended, responding instantly and accurately to command changes. Moving on to efficiency, the 4 quadrant drives significantly reduce energy wastage. This is largely thanks to regenerative braking, a feature that allows systems to recover energy during braking instead of losing it as heat. This recovered energy can then be reused within the system, leading to substantial cost savings and environmental benefits. In industries with high power demands such as transportation and heavy manufacturing, the impact on both the operational cost and sustainability is very important. Lastly, if we see the operational flexibility, The 4-quadrant operation allows machines to quickly adapt to changes in processing tasks without the need to pause or stop. This adaptability is crucial in modern production environments which demand versatility and continuous operation. Whether adjusting to different material loads or switching between the production modes, the ability to maintain continuous and efficient production without downtime has become a real game changer. So, in conclusion, the integration of 4-quadrant operation into drive systems transforms how industries manage and optimize their machinery. It's not just about improving individual tasks but enhancing the entire production ecosystem. Now let us discuss the technical backbone of 4-quadrant drives. Understanding the components and their roles is important for grasping how these drives manage complex tasks with high efficiency. Let's start with the converters. These are not just simple power converters in a 4-quadrant setup, they are dynamic, capable of reversing the power flow. This functionality is vital for enabling the motor to switch between motoring to braking and forward to reverse operations smoothly. By manipulating the direction and the nature of the current, converters allow the drive to exploit the motor's full capabilities across all the 4 quadrants. Next, we have controllers. The controllers, we can say, are the brains of the operation. Controllers use sophisticated algorithms to direct the converters and motors, dictating speed, direction and torque based on real-time inputs and preset conditions. Their ability to process inputs in a very fast manner and adjust outputs also allows for seamless transitions between operating mode, and this is very critical in applications that demand again high precision and adaptability. Finally, the feedback mechanisms. These components are the sensory organs of the drive system, whether it's speed sensor, torque sensor or position encoders. Feedback mechanisms provide the necessary data to the controller. This continuous loop of feedback and adjustment is what makes modern drives incredibly responsive and precise. This is the reason a vehicle can efficiently convert kinetic energy back to electrical energy during braking, or why a robotic arm can adjust its motion instantly to correct errors. In essence, we can say that the synergy between converters, controllers and feedback mechanisms in the 4-quadrant drives allows for unparalleled control and efficiency. These systems do not just react, they anticipate and adapt, ensuring optimal performance across a wide range of demanding applications. Let us now see the advanced control strategies used in 4-quadrant operations, specifically the vector control and the direct torque control. Both the techniques play crucial roles in enhancing the performance and the efficiency of the modern drive systems. Let's start with the vector control. The vector control method allows us precise management of the motor's magnetic fields, which is important for applications that require exact speed and torque adjustments, such as in automated assembly lines or in vehicles. The main advantage of vector control is its ability to maintain optimal performance throughout the motor's entire operating range, thus maximizing its efficiency. However, if we want to implement vector control, it can be complex as it requires detailed modeling of the motor and its response to achieve the right setting for the control algorithms. Moving on to direct torque control, also known as DTC, is a method which is known for its quick time responses. Especially this is useful in situations where load conditions change abruptly. Think of elevator systems or cranes where load can vary significantly in a very short span of time. So, DTC makes the speed control simpler because it does not need pulse width modulators, making it easier to set up than the previous one, that is a vector control. However, it also have some challenges, and the main problems are that it can cause more torque fluctuations and the frequency of switching can vary, which might disrupt the smooth running of the drive. As we conclude today's lecture on the 4-quadrant operation of the drives, let's briefly review what we have learned and consider the implications of this technology in both current and future applications. We began with the basics of torque equation, understanding the bidirectional electric drive systems. We then delved into the core concept of the 4-quadrant operation, exploring how this capability is integral to modern drive systems, allowing for more precise and versatile control of the motor operation. We also discussed the importance of 4-quadrant operation and its industrial significance, its technical components that make these operations possible, including converters and controllers, and how they work together to achieve seamless transitions between different operational modes. Our exploration of control strategies such as vector control and direct torque control highlighted how these approaches enhance the system's responsiveness and efficiency. Thank you for your attention.